Is this thing on? Yeah. So, usually I start this talk by asking the audience whether they know the difference between SSL and TLS. After this week, I will kind of skip this part because I assume you all know. And without further ado, cześć, I'm Hynek. You may know me from the internet where I look like this and squat basically all the Hynek accounts all over the internet. When I'm not conferencing, open sourcing, or yelling at the internet, I'm doing, as already said, infrastructure at a small German-based web hosting company and domain registrar. Unfortunately, we only serve the German-speaking market, so I can skip the advertising and get to the talk right away. So, why I'm here? I'm here to tell you that those shiny lock icons that tell you that you're safe because of military-grade encryption are a lie. In fact, you never really are safe, and while this statement may have been a bit more controversial like 2 years ago, I can assure you that nothing really changed with Snowden, Heartbleed, and all those other vulnerabilities, because this all has been common knowledge between people who were interested in these matters, but nobody cared. HTTPS was just there in the browsers, OpenSSL is open source software. What could possibly go wrong? So, turns out a lot. But before we go into deep, this is the only link you have to write down for today. It's also the only link I will show to you. It will contain all the links, all the projects, all the concepts I will talk about. So, yeah, relax, enjoy the show. And so why is the state of SSL sorry? Kind of a rhetoric question by now, but we'll still start at ground zero and explain what SSL actually is and what the hell has it to do with TLS. And I find those terms are best explained in a short history lesson because everybody loves history lessons. And our particular one starts in the mid-90s when Netscape started to think that it might be kind of cool if paying by credit card on the internet did not entail people spending your money on other things. So they made up HTTPS, and the underlying technology was called Secure Circuit Layer 2 or SSL2, which was a complete disaster security-wise. So 1 year later, the worst things were fixed with SSL3. And yeah, you may have heard of it this week. And another 3 years later, we are still in the 90s. Another 3 years later, after a brief fight with Microsoft, finally a final internet standard has been proposed called TLS, Transport Layer Security. So again, SSL is a product from Netscape from 1996. TLS is an internet standard for 15 years now. And if you follow IT news again, you should know that the product from Netscape has been killed by a rabid poodle just recently. So, again, basically tricked you here with the name. Nevertheless, everyone knows alliterations are always awesome, and I wanted to reach as many people as possible, so if I had to trick in here, you hopefully learned the first thing today and will not say SSL in the future, because it unnerves me incredibly. So, 2006 and 2008, the history continues, and the largely ignored TLS 1.1 and 1.2 have been released, but nobody gave a bloody damn. Fast forward to last year. For some totally random reason, people started to scrutinizing our security habits again, and what they found was not very good. So for one, all mainstream browsers supported only TLS1 until last year, so TLS1 from 1999. The discoveries in 2013, though, changed basically everything, and the times where you just said, I'm using TLS, I'm fine, or I click a checkbox with an SSL sign on it, they are gone. People have realized that this technology has very sharp edges, and getting it wrong can have very, very grave consequences, like people can literally get killed if you fuck up your SSL. So, what is TLS? What I actually want to give to you? It's basically 3 things. First, there's peer identity using certificates. You can verify that the host you're connecting to is actually the host you hope it is, and not some crook who tricked you to connect to them and just read everything you exchange. So, therefore it protects you against so-called man-in-the-middle or MITM attacks. It gives you also confidentiality. which is basically encryption. This is what most people think about when they hear about HTTPS, SSL, or cryptography in general. So you cannot read what the peers are exchanging because it's encrypted. So, and finally, it gives you message integrity using message authentication codes, and that ensures that you can detect if TLS records arrive out of order multiple times or not at all, which is just as important as the other two parts. So now let's see how to use all those three and explain further details along the way. After this part, you will be able to detect the worst smells of TLS usage and hopefully avoid them in your future. And we will start with servers. And unless noted, I will stick to OpenSSL for now because that's what you will most likely be using. And if you deploy server software, it's your duty and nobody else's to ensure as much security as possible for all of your users because they can neither see nor affect your setup. So the first step is to use at least halfway up-to-date software, like third-party software. So if you deploy anything older than this, you are being negligent, lazy, and should stop doing so. And I'm nice enough to assume that they are using a distribution that backports security patches, because these are version baselines. Like you need this version with the feature to have the features you need to have a secure TLS setup. If you're compiling your stuff yourself, you all have to have the latest versions, of course. Otherwise, you will have bleeding hearts, and angry poodles. So the first thing you do when a client connects to you is that you present them a certificate, a kind of ID, which says who you are, which the client should verify. So in order to make the client actually trust the certificate, it has to be signed by a trusted third party called a certificate authority, or in short, CA. Now, each client has a database of all certificate authorities they trust. It's called the trust database, or keyring. It basically depends. This database can also be part of the browser, or part of the operating system, or just part of some package. So it depends. There is no unified way for that. So, this is something you send out to everyone. So there needs to be a way to verify that you're the rightful holder of this ID, of the certificate. So a secret key belongs to each certificate. And using that, you create signatures, which then can be verified using the certificate. So it's proven that this certificate is from you. And basically, that's all there is to know about certificates. It's information about validity that is signed by a trusted third party. That's all. Your job now is to make sure that your certificate setup is trustworthy, because TLS is really worthless if the clients have no chance to verify that you are who you claim to are. And you will not get a certificate which is signed directly by a trusted third party. Instead, you will get a so-called chain file along with your certificate. So, in this case, the trusted CA at trust signed some certificate from Komodo, which signed another Komodo certificate, which finally signed my certificate. So, whenever a client connects, my web server sends out all three certificates. So, take care of a trust chain. Forgetting chain certificates is a typical rookie mistake. Ensure that the certificate is actually valid for the hostname. And of course, make sure that your certificates aren't expired. Then, disable SSL2. Chances are that's not necessary, because usually if you get an installation of OpenSSL nowadays, SSL2 is not compiled into it at all. The code is gone. But of course, the OS X OpenSSL still ships with SSL2 support, which is kind of bad. And I really hope nobody of you is deploying server applications on OS X, so it shouldn't be a big of a problem. Then disable TLS compression to avoid crime attacks, and finally disable SSL3, or this guy is gonna come over and hurt you. And the dust hasn't really settled by now about what the implications are of this attack. But one thing is clear, that by disabling SSL3, you do not kill off only IE6 like many articles are claiming. You are also killing off IE8 or any Internet Explorer that's running on Windows XP. The reasons, I'm not quite sure, I hadn't time to investigate, but it's some handshake thingy, and yeah. So that's important to know. It's not only about IE6, it's about Windows XP in general, although you can use Firefox or Chrome on Windows XP and it works just fine. So the next objective is to configure your CIPHER suite such that every client gets the best possible encryption. And a CIPHER suite is just a tuple of multiple cryptographic primitives or algorithms that are used together to ensure the security of a connection. And ultimately, the server has the last say about which suite is used, so use that power for good. So we start with the ciphers, which by itself are the most straightforward thing. You can imagine them like black boxes, and they take a plain text and a key as input and return a ciphertext that should be indistinguishable from random data as output. And TLS ciphers are symmetric. That means in order to get from the ciphertext to the plain text, you will need the exact same key. This is pretty important for later. So far, this is rather straightforward. It gets more complicated because most ciphers that are used nowadays are block-oriented. So you cannot just pass in a 1 GB movie into it and call it a day. You have to chop it up to the block size of the cipher, which for AES, for example, is 128-bit. And of course, if the last block is smaller, you have to pad it. So the most common way to do that is so-called cipher blockchaining, which unfortunately was implemented really poorly in TLS, which bestowed us with a wide variety of attacks. Poodle is one of them, by the way. It's just a mode problem, in fact. So the widely ignored TLS 1.1 fixed that, but nobody cared. So the alternatives are basically using stream ciphers like RC4 in the past or Cha-Cha-20 in the future, or client-side fixes, which is essentially what happened. And finally, TLS 1.2 brought a shiny new mode, which is called the Galois counter mode, but more on that one later. So we know what the cipher are, which one to use. So this is a topic of quite contention. You can discuss for hours and days about which one is best, or to put it different, which one is the least bad. At some point you have to make a call. So I'm gonna just use what Google is suggesting or actually using, because they are basically the one company who is pushing the TLS security at the moment most in the world. So I'm gonna say that AES 128 in Galois counter mode is the best block cipher, and Cha-Cha-20 is currently the best stream cipher from Dan Bernstein. So AES GCM is better in hardware. There are some nice chips for that, and Cha-Cha-20 is really nice in software. So ideally you would support both, and if the client supports, if the client has hardware support, you would use that, and Cha-Cha-20 if not. And this is exactly what Google does, but unfortunately it's not available to us mere mortals, so AES GCM it is for now. Even for the latest for the latest Safari and IE browsers, you will still have to fall back to AES 128 CBC, which in fact is fine for TLS 1.1 and 1.2, but it's a train wreck for TLS 1. But you don't have really much choice, so you can just hope that the clients will have the client-side fixes for all the problems that are piling up. Finally, if you need to support ancient clients, I would suggest SSS, which is a decent cipher. The only problem is that it's terribly slow, because the 3 means that the DS cipher is used 3 times. So that's not the most effective way to encrypt or decrypt data. The question is, and I'm not 100% sure about that because the situation is evolving at the moment, whether you need it at all by now. If you disable SSL 3, it's quite possible that you also cut off all the clients that used to need SSS before. But we will see. So, but definitely that's it. You don't need anything else to support everything you will encounter on the net. And be especially wary of the following ones. So, export ciphers. They were intentionally weakened in times when the there was severe restrictions on the export of cryptographic software from the United States. So they have a backdoor by design. Don't use them. DES is an ancient cipher. Has 56-bit keys, and it can be probably cracked by your phone. So don't use it either. RC4 is kind of more complicated, except it isn't. Some people still consider it as a silver bullet for mode-based problems because, again, it's a stream cipher, so that it does not have all these problems with block, with chopping and padding. However, basically all cryptographers I'm aware of were claiming for years that it's a really bad cipher and that state agencies probably will be able to decipher the text, like in a passive way. So they just capture it and then later they can decipher it. And turns out they were right. So I'm not sure about the real-time thing. That seems pretty ambitious, but definitely don't use RC4. Don't let anyone tell you anything else. It's really bad. So in order to encrypt and decrypt, we need a key. And as we've already established, the key has to be the same on both sides. Actually, there are several keys involved, but I'm going to ignore it for the sake of simplicity. So we have an unencrypted encryption, unencrypted connection, and we know to exchange keys to encrypt it, which kind of sounds like a chicken-egg problem. But fortunately, math came to the rescue and gave us no less than 3 ways to exchange keys in a secure way over an unencrypted connection. So first there's RSA, which is both a corrupt company and a public key crypto system. So we have a public key and a secret key. You encrypt with a public key, you decrypt with a secret key. Simple. It is fast. That's why people really liked it in the past. But as soon as the secret server key bleeds out of the server, you have a problem. Because all communication that ever happened right now and will happen can be decrypted. So basically, any connection data that is created over an RSA, over a connection where the key has been established using RSA are a time bomb. Because if you capture them and 10 years later you somehow get the server key, you can decrypt everything you've ever captured. So it's really bad. So ephemeral Diffie-Hellman. This is PFS. Oh, I didn't explain. So we call this perfect forward secrecy, which basically means that what I just described does not apply. So getting the server key does not mean that you can decrypt everything you've ever captured. DHE does have this property. So if you exchange keys using DHE, you're fine. But it's slow. So although it has been around for a decade or so, it still hasn't been used very much because it's slower. So there's a solution to that, fortunately, which is the latest edition called ECDHE, which is the elliptic crypto version of DHE, which is both fast and perfect forward secure. So, and I would like to stress again, make sure that you get perfect forward secrecy for as many clients as possible. It's one of the most important parts, and it's one of the most easiest to get wrong. And for that, you will currently use both DHE and ECDHE. And since ECDHE is much faster, I would suggest to prefer that. So, finally, the third part is message authentication, which is done using message authentication codes, or MACs. In this case, a message is just a TLS record or some lump of data that's getting sent around. They are not, by any measure, TLS specific. And they combine some magic crypto dust with shared secret keys. And so they ensure both the integrity and the authenticity of a message. So that means that if you get a correctly signed message, you can be sure that it has been sent by the person who has the shared secret key, and it was also sent in that order. TLS uses a so-called keyed hash MAC, or just HMAC by default, and before that SSL used something similar but different. If your connection is secured by a traditional cipher which uses an HMAC, you can affect which cryptographic hashing algorithm is used for that. And there is nothing really you can do wrong, but I like to disable MD5 HMACs because they irk me. So they don't suffer from the usual MD5 problems. They are basically fine, but I don't think any solid crypto system should have anything that has MD5 on it. So, finally, TLS 1.2 introduced the possibility that ciphers bring their own message authentication with them. So, and this is where the aforementioned Galois counter mode shines, because it has message authentication as part of the cipher. So then it is implemented in hardware, and then it's really, really fast. Plus, it doesn't have all the problems we heard before. So it doesn't make the authentication part a separate step, but it's integral. So finally, if your list does not contain only strong PFS ciphers, make sure that your own cipher preferences are the one that used and not the client's one. Because the most up-to-date TLS implementations will buy you nothing if the client sends you some really funky cipher list and you obey. For example, IE is notorious for that. Even in the latest versions, their preference list is bizarre. It doesn't make any sense. And then you're done. If you do everything I've told you on the past slides, you're fine and way ahead of the pack. And everything else is mostly just minutia. However, thinking that you've got it right means absolutely nothing. You have to test your results. Because there's some really confusing stuff that can happen, like rel/CentOS 6.5 will give you an OpenSSL that happily does ECDHE. However, their Nginx is compiled against an older version, so they are not going to be exposed to the clients. So you have to really test it from the outside. And if your server is HTTPS, which is quite common, I'm gonna assume, you're lucky because there is a nice service for that to test it. It's the Qualys SSL server test. So I will just use the results now of my homepage to show you how to read their output. And I would like to stress that I will show only a subset of things that are most important. So if you're working on the security of your site, return and make sure you get everything green. An A+ is really not that hard to get. So, first a certificate. Nice VGA graphics. I hope it's not too blurry. So the certificate is valid for my homepage, both with and without www. It's valid from this March until next May. And the key is a 4K RSA key. It means it uses RSA for cryptographic signatures, not for key exchange. It's the same algorithm, but a different use case with wildly different implications. So other possibilities here are DSS, which literally nobody uses, and ECDSA, which is kind of trying to come up, but at the moment I basically know only of Google who's using it. Which also means that you have to go for dual certificate setup if you want to offer ECDSA. So, as for RSA, 4K is the current state of the art, 2K is okay, and 1K is a serious security problem. So it was issued by the Komodo CA. It uses SHA-2 with RSA, which is nice. You should go for SHA-2 certificates nowadays. You will get warnings in browsers, I think, pretty soon. It does not have extended validation, which means that you get your name into the browser bar, because I don't support this kind of racket. And it's not revoked. Nice. Next up, protocols. Ensure that TLS 1.2 and 1.1 are active. And SSL 2 and 3 inactive. Finally, there's still TLS 1.0. It's a sad fact of life. Everybody would like to get rid of it, but you really can't. It's not practical at the moment, so vodka helps. So now let's look at the complete Cypher suite. And here it is, the currently best widely supported Cypher suite. You want to have it up there. And it uses the aforementioned ECDHE, which is fast and forward secure for key exchange. It uses RSA for signatures, which is something which is dictated by my certificate. It's not something you can choose. And yeah, it uses AES 128 in GCM mode. And finally, it uses SHA-256, which is from the SHA-2 family, for key derivation on handshake. If this would have been a classical CBC cipher, the hashing function would be also used for the HMAC. So, as you can see, my server strongly prefers perfectly forward secure ciphers against those that are not. So this is kind of important. Those again are mostly just for old Internet Explorers. So if time shows, maybe we'll be able to drop them too. Now we've dropped SSL 3. This is really something that's in motion, but yeah. Next up, client software. And turns out that that browsers explicitly aside the client side of TLS is in the worst shape of them all, which is kind of odd because they really have one job: verify. Verify the certificate the server sends you. Is it valid or is it expired? Is the chain trustworthy? And finally, is it even valid for the hostname you wanted to connect to? Especially hostname verification is in a pathetic state. There's even scientific papers about how software does not verify hostnames. And unfortunately, OpenSSL has no little part in this status quo. So you'll start with a trust chain. So the first thing is that certificate verification is opt-in. And guess what? You have to tell OpenSSL explicitly which CAs you trust. Unfortunately, trust stores are highly platform dependent. Every OS has it elsewhere. So fortunately, there is a function which will read the CIs from compiled in path, but for some odd reason it's absolutely not documented anywhere. And it also only works with trust databases that are file or directory based. So if you're on Windows or on a Mac, there's a problem. And as with OpenSSL's obstacles were bad enough, operating systems vendors are also nice to you because they don't install their CA databases often. So for FreeBSD, you need CA root NSS. On Red Hat-based systems and Debian ones, it's CA certificates. So make sure you have them before you try to verify certificates. It will fail otherwise. On OS X, you can either use the one which is shipped by Apple, which has a patched-in trust evaluation, a TEA, which basically intercepts the certificate validation and does its own thing with very surprising results. It cost me a week of my life to figure it out. Or you just use Homebrew, which will create a copy of your system trust database and create one for its OpenSSL. So it's frozen in time, but it's still better than the alternatives. For Windows, there's the Win-Cert store on PyPI, and if you want to just skip all of this, you can also use Certify, which is a Python package of Mozilla's trust database. So, again, the situation is much, much worse when it comes to hostname verification, because OpenSSL here just says there's frankly absolutely no assistance from OpenSSL whatsoever to check whether a certificate is valid for a hostname. There is not even documentation on that. So everyone has to implement it themselves using RFCs and bogus advice on Stack Overflow. And as you may imagine, it's raining security bugs and CVEs. Python has a few of them too. So, but failing to verify the certificate and hostnames makes you extremely susceptible to man-in-the-middle attacks. So if you don't verify certificates at all, which is the default, I can pretend to be Google for you with a self-signed certificate I can create in a few seconds. If you phone the APIs to verify certificates, but don't compare host names, I can still be a Google. I'll just use the certificate for my own host name, for my homepage, which is perfectly valid, just not for the host name, but you will not know because you didn't check. So, if there's only one thing you take away from this talk, please let it be this: verify all the things. Because the rest is rather mundane. Limit your acceptable ciphers to strong ones for times of poorly configured servers, and disable SSL2 and SSL3. And that's all. Yet so few do it, which is like a perfect storm of ignorance on the one side and the lack of APIs and documentation on the other. So, and we will finish with the weakest link of the security chain, the users. They may make everything fall apart, no matter how much the rest tries to keep them secure. And it starts with fundamental misconceptions about what TLS actually want to do for you. So for example, it's nice that your connection to your chat or email server is secured by the latest and greatest cipher. That's great. That will protect you from eavesdroppers stealing your passwords. Keep doing it, please. But if the other person is connected using plaintext, or one of the servers is compromised, which happened just a few weeks ago on Freenode, the confidentiality for this conversation is 0. And since there's no way for you to know this, you have to always assume the worst. So TLS only offers security between direct hosts. If you need end-to-end encryption or end-to-end security, you will need something else, like OTR for chat or PGP for email. And then there's the problem that certain data just can't be encrypted. So if you serve a job site at your workplace over HTTPS, IT can still find out what you're doing because of job patterns and DNS queries and whatnot. You will have to use a VPN for that. But a VPN routes all your traffic through the network of your VPN provider, so better make sure you trust them. And this, by the way, just as well applies to CDN providers. It's even worse, because CDN providers do the TLS termination for their customers. So basically, they can see all your data in clear text. So Fastly could sniff all your PyPI passwords if they wanted to. And this is, again, so important to never reuse passwords, because you never get to know who will see those at some point. So, if you've ever clicked away such a certificate warning without double-checking what's going on, you may have been MITM'd. The rule is rather simple. Investigate the warning, and if you don't 100% understand what's going on, decline. Yeah. So typical things are expired things, like if the certificate's expired today and everything else is fine, you're probably fine too. Or like in this case, if it's an open source project which haven't yet properly implemented SNI, you're probably fine too. But if you don't understand what's going on, really decline. Man-in-the-middle attacks are trivial to pull off, especially on like open networks like here on Wi-Fi's. It really all it takes is a rogue DHCP server. The next level of clicking mindlessly is if some crook tricks you into installing their root certificate into your trust database, which, by the way, on iOS is sometimes called profiles. So if you've ever installed profiles into your iPhone, you may want to double check what happened there. It means that every certificate that is signed by them will be considered trustworthy in the future. So you will never ever see a warning again if they MITM you. Except if their CA gets blacklisted at some point in browsers, which is kind of the only way we protect each other at the moment. So, and speaking of trust databases, even if the user does not screw up, there's a lot that can go wrong. So, they are what the browser queries when it tries to determine whether the chain it just got is ultimately signed by a trustworthy CA. And it happens to be true that the default trust databases contain entities which may cause some level of discomfort to you. This just means that the Department of Defense of the United States of America can sign any certificate they want in the world, and it will be trustworthy. And it's not like China is standing back or anyone else. Every country has a CA they can abuse for their nefarious things. And it's also not unheard of CAs being hacked, making fatal mistakes, being forced to cooperate with authorities, or simply belonging to corporations which may have priorities that don't quite match yours. So for example, Google and Microsoft are both CAs. So just whatever you make out of it. So this whole system is completely broken. And speaking of broken, let's talk about Python next. Let's start with a very simple rule of thumb. As you've seen, it's really easy to screw up TLS. So if you can, do not try to do it yourself. Use battle-tested software like Nginx or Apache and put it in front of your applications. Do not try to be too smart. But since life usually isn't that simple, I will talk about how to do tails anyway. So the Python world is basically divided into two camps. There's the SSL module in a standard library, and there's PyOpenSSL. And that sounds simple enough, but actually it's pretty complicated. So let's break it down, and we'll start with the standard library first. As a rule of thumb, everything that came with and after Python 3.3 is fine. Although you still have to be careful because of backwards compatibility reasons, the defaults are still terrible. So you still have to know what you're doing there. So for example, hostname verification is off by default in Python 3.4 because everything would break if we would start verifying hostnames suddenly. So that's a situation you will wish for in Python 2 because its coverage of OpenSSL APIs is very, very poor. So it's impossible, like literally impossible, to write forward secure servers with the standard library's SSL module. So basically, you shouldn't write TLS servers using the standard library at all. It also lacks a bunch of options, so you're bound to the OpenSSL of your Python that has been compiled against, which is also not so nice. However, after a lengthy discussion, the core team came to the conclusion that having a completely broken SSL module in the standard library is kind of a security problem, and should be treated as such. And so, under the guidance of Nick Coughlin, it happened that Alex Gaynor and David Reed backported many of the important features from Python 3. The thing is, it's not out yet. It will be part of, it's already merged, the patch is in there, but it has to be released as of Python 2.7.9. Although, one more complication, Fedora Rawhide and Debian Jesse already have backported that patch into their own 2.7.8. So that makes things more complicated, but at least you get an idea how important these changes are. What's also missing is hostname verification. So it's backported and it's in there from 3.2 on. Everything older than that, you will have to install a backport that is on PyPI, fortunately. However, you have to remember to actually install and use it. So everything's opt-in. So, PyOpenSSL. It predates the SSL module in the current form, and it runs currently on all relevant Python versions. And although it has been dormant over the years, it still has a much better coverage of OpenSSL APIs than the standard library in Python 2. More importantly, a new project gave it a new vigor, PyCon cryptography. I don't know if anyone already heard about it because now the project is already like a year old or something, but it's a bunch of people with more time than sense and a knack for bad life's decision, and we just decided to write a Python library without foot guns. So eventually we gave us a name, and it's the Python Cryptography Authority, which is inspired by PyPA, which is the Python Packaging Authority. And yeah, a side product of that crypto library are PyPI-friendly CFFI bindings for OpenSSL. And you can compile it against any OpenSSL you want on your system, which is also really, really nice. And that made PyOpenSSL just throw out all their C code, and it gave it some serious momentum. So as of now, PyOpenSSL is a pure Python project, and all the C stuff, C magic that's happening in cryptography. What unfortunately is still missing is hostname verification again. So, help is on PyPI. Service identity gives you just that, plus some more obscure ways to verify the identity of a server, which nobody really does, but it's in the RFC, so if you're interested, you can use it. Again, it's completely opt-in. You have to know what you're doing. So we will look next at some common frameworks and packages, how well-behaved TLS citizens they are. Yeah. Let's start with servers again. And EventLand, GEvent, GUnicorn, and Tornado all suffer from the very same problem. They are using the standard library, thus it's literally impossible to them to be to offer PFS ciphers, to offer good defaults, or to be configurable in the first place. Tornado, which is also a Python 3 project, could do it on Python 3, but they don't. And GEvent just added some code for Python 3 recently, but as far as I know, the last time I looked, it hasn't been part of a release yet. Yeah. So, Twisted. Twisted is probably one of the few legit reasons to actually do TLS yourself, because it's used to implement much more than just some web applications. So it's quite simple. Put an Nginx in front of all of them except Twisted. And it's important to note that these check marks are only valid for the recentish version 14.0, because before that the TLS support of Twisted was pretty bad too, and it took us a year to fix it. What's also a little known fact is that Twisted comes with a pretty nice Whiskey container. So in other words, you can deploy Python web applications using Twisted and not put anything in front of it and still have great TLS support. And no, deploying Whiskey apps on Twisted does not mean that you have to use callbacks or camel case. It's all good. And then finally Micro Whiskey, which is not, despite the convincing name, a Python-specific project. And so they went on and wrote some C themselves, which kind of paid off, as you see. However, I would still always put an Nginx in front of it, because I just don't trust C code that uses OpenSSL. There's just too much that can go wrong. So now, contrary to when I held this talk the first time in Montreal in April, there is hope for these daggers. And that's when the aforementioned PEP 466 lands and Python 2.7.9 is released. So we can only hope that the project maintainers then will embrace it and fix their TLS. So, clients. EventLand and GEvent are just the same, although it is possible to do better, and Tornado shows the way. They use the hostname matching backport, and they depend on certify. And they verify both by default, which is the right way. But on the other hand, they run into problems like the inability to disable SSL2, because that has been added in Python 3.2, and that causes some really funky errors if you are using a Tornado application as a HTTP client, HTTPS client on OS X. So Twisted again got much better with 14.0. All the low-level parts are in place, and some of the higher parts are doing well too. For example, the HTTP agent does everything correctly by default. By extension, it means that our own request clones called track also does everything the right way. However, for the plumbing and the lower things, no, the plumbing is in place, but the higher level connection endpoints still don't do the right thing by default. It's something we have yet to fix, but we are on it, and we take this all we name this very seriously. But it is possible to write secure software, secure client software with Twisted. So what's probably not be good is URL 2, which does not verify anything. You cannot change anything. If you ever have to open HTTPS URL, don't use it. Instead, use requests, which some people think that's great because of its API. I couldn't care less about the API. What I like about it most is that it goes great lengths using URL 3 to do the right thing by default. So for example, Certify I've talked before, which is the package of Mozilla Trust databases, has been born as part of requests to enable easy certificate checking in Python. So, and the thing is, if you install PyOpenSSL and some other modules, you get really, really great HTTPS support. So, let me sum up. Keep TLS out of Python if you can. Use requests for HTTP queries. Make sure you are using the PyOpenSSL backed version. If you know what you're doing, you should use URLib3 because you're less likely to run into some compatibility problems. We really need less libraries that depend on requests because sometimes it can be really painful. Write TLS servers in Twisted until 2.7.9 because it's the only way to write secure TLS servers in Python. After 2.7.9 because it's the best way to write network software in Python. As of now, if you need low-level TLS, use the latest version of PyOpenSSL. It is greatly superior to Python 2's ones, and it will follow you faithfully if you ever port to Python 3. And finally, until we got our fixes in hand, use Python's 2 standard library only for clients. And whatever alternative you choose, make sure that you use the relevant packages to verify host names. So, nearly done. I would like to answer the question from the very beginning. Why is the state of SSL sorry? It's sorry because people still say SSL, although the technology has been obsolete for 15 years now. It's sorry because the implementations are terrible. All of them. It's sorry because users run outdated software, click certificate warnings away, and are at the mercy of third parties. And of course, those third parties let them down regularly. Servers run completely outdated software, and I'm really curious how the bar around SSL 3 will change to the next month. That is configured completely poorly. Clients don't verify anything, although it's their only job. So in January, the security researchers from IOActive found that 40% of online banking applications have been susceptible to MITM attacks. That's pretty bad. And finally, it's sorry because Python is at the forefront of being terrible. The current state really still is sorry. It's a bit less sorry than it was in April, but it's still very sorry. The title of this talk is no bait. So, but there is really hope. First of all, people started caring again. And as any alcoholic can tell you, acceptance is the first step. Standard libs TLS support got much better since the Python 3.3 release. So if you ever need a reason for Python 3, there you go. And it also got pretty fine now through PEP 466. So there goes your Python 3 argument again. I've already mentioned PyCon. It's a bunch of really smart people, plus me, and we've already adopted several crypto-related projects, and ultimately it's supposed to be the one-stop for solid crypto software in the Python universe. And this is a really huge deal, because the standard library really moves too slowly to react to the realities of security and TLS. So, hope always means work. So, therefore, I have a few calls to action to all of you. First of all, stop believing that a log makes you and your data safe. Be a critical user. Do not click away certificate warnings. Do not install rogue root certificates. Configure your servers properly. Install security updates immediately. If you connect to servers, validate all the things. Certificates, host names, all of them. And finally, help us to get Python out of this mess. Fix your libraries, fix your software, file bugs against other libraries, help other libraries be fixed. There's still a lot to do, and there will be even more to do after the SSL backports will land with 2.7.9. And yeah, that's all I had for you today. I hope you learned something, and more importantly, are eager to fix now. So go out, study the talk page, and get your domains from Wikimedia if you speak German. Thank you.
Okay, so there's a small announcement. The talk by Wojtek Erbatowski, designing API for mobile apps, is moved from today to tomorrow. And after the year, we'll have a talk by Flavio Bracocco about systems integration and OpenStack. So now there's time for questions.
Actually, it's not a question. You said that right now only Google is using ECDSA for signing certificates, but recently Cloudflare released their new product, Universal SSL, and they are giving they are CDN and they are giving SSL for free for all of their customers. They use also ECDSA. This is, not very important, but there's something like 2 million websites with this, and the more important thing is that I think developers, companies running some services should stop doing things like our organizers did. So, for example, when you were registering for this conference, there was self-signed certificate on the registration form. So, if you don't want to spend money for certificates, it's much better to use a service like Cloudflare with their universal SSL and have SSL for free. So,
yeah, there are definitely ways to get free SSL in the world. I think like Rapid SSL was giving out free certificates too. But yeah, I don't really think that's a pressing problem, this ECDSA thing. But yeah. It doesn't really solve so much of a problem. So therefore, the uptake is much slower than example ECDHE, which really was taken up pretty quickly because DHE is really slow. And RSA is shitty. So.
So, hello, Roman. You showed the table which compares some implementations of some stuff security in different web servers or web frameworks. But there is also one like very popular framework which is called Flask, which uses vector server.
You mean Flask?
Flask, yes. So,
okay.
Did you have a chance to review that?
You use Flask, as far as I know, uses some other server underneath. So
it's called Werkzeug. I think.
Come again?
I think it's called Werkzeug. It's something in German.
Yeah, Werkzeug is a whiskey server. I don't think it really does HTTPS itself. I'm not sure about that one. But you usually always put a proxy in front of it. That's the right thing to do. So I'm not 100% sure what Flask does by default, and Armin usually knows what he's doing, so I would not expect that he does something really dumb with it. But I remember that most deployment guides for Flask were about using Gunicorn or something, and Gunicorn is terrible at this point.
Thank you.
Hi. Oh, hi. I've got a question. It's not really technical or related to SSL and Python directly, but do you think that it's a good idea for the SSL to exist on the application layer? Shouldn't it be provided like below? Like I ask for a socket, connect, something underneath verifies everything for me as a developer, and then either fails because it was wrong, or I get a secure connection.
Yeah, you're basically asking me whether the internet should be encrypted by default, and the answer is yes.
Okay, thanks.
Any more questions?